So the next speech will be by Professor Ludovic Righetti. So please go ahead.
Hi, everyone. Yeah, thanks for inviting me. So thanks for inviting me, and yeah, thanks for organizing the conference. I've been having a lot of fun so far, so that's great. Is locomotion a solved algorithmic problem? Let me answer the question right away. I have no idea. No, so I think probably not. We never solve really a problem, right? There's always something new that you can do. But what I thought was really surprising to me, actually, was maybe a revelation to me, is that at ICRA this year at Yokohama, there were so many leg robots, and they all are doing so many amazing things, right? They're all walking around. They are they're very robust at doing that. And I was starting to think, what happened, right? How is it that we have suddenly so many cool robots doing so many amazing things? And so how did we get there? So I'd like to spend this next few minutes to try to tell you what I think were the important ingredients, how we got there. And maybe as a disclaimer, I will mostly show things that are my work, so videos from my team. But all the things I will show, obviously, there's a lot of other people that have nothing to do with me, right? They've done amazing work, and so I don't mean to claim that I invented all the things, all the ideas that I'm going to show today. Okay, so how did we get there? So I looked at the things that I've done. My first ICRA paper was in 2006 in Orlando, and I was fortunate to work with a humanoid robot at EPFL, the Hope 2 from Fujitsu. And as you can see, the way I'm holding the robot, this is not working really well, right? Actually, it was mostly falling. So this is the one shot where it actually worked. It's on the video. So I was thinking, okay, so things were not really working really well in 2006, but it's not really true, right? I was actually pretty late to the party, which I think I always felt a bit like that since I started my career, right? Asimo was running right in 2004, was at the university, had humanoids working with ZMB control since the 1984. Kajita had already written all of his groundbreaking papers on working, like the linear inverted pendulum model, preview control of angular momentum. And in 2006, I also realized while preparing this talk, that's the year where the idea of a capture point that was published by Jerry Pratt, this idea of what is the point on the ground if you're walking where you could step and come to a stop instantaneously. This had a huge impact in our field and how we design controllers. And another thing that was also published in 2006 is the first paper on how you can do linear model predictive control for walking by Pierre-Brice Weber. So all the ideas, or at least all the really important ideas and all the modeling and understanding of walking was kind of there at the time. So why didn't we see a burgeoning of robots, of walking robots then? And I think there's two reasons. One is maybe algorithmic, is that robots were not capable of adapting their behavior in real time. So that's the first problem. It means that if things would happen unexpectedly, basically robots would fall. And the second thing is that leg robotics was a closed club. Very few people actually had access to leg robots, right? Either if you wanted to do leg locomotion research, either you had to build your own robot, which is very complicated, or you had to have a lot of money to be able to buy one, and very few companies actually would sell you one, right? What people were doing, why did robots were not able to adapt is because most of the thing was done offline, right? You would plan things relatively offline. You would have some pattern generators, and then you would send it to your controller, and you had some sort of PD control and a stabilizer that would follow some trajectories. So then if something would happen, then we didn't know how to adapt the behavior of the robot on the fly. And one of the things that really changed the game, I think, is when we realized and we started to have mature optimizers and realized we could put them in control loops. So suddenly, instead of having a controller, you have an optimizer that behaves as a controller. And we started to do so people in the community started to use quadratic programs, right, to solve control problems, and then you start to be able to add constraints, to say, well, I want my robots to apply a certain force on the ground, and I need to have some stability constraints on what the foot is going to do, and I want my center of mass to move a certain way. You give it to your solver, and your solver tells you how you need to, what kind of acceleration the robot should have, and what kind of torques you should apply on the robot. Of course, you also need to have torque control robots. This is a really important thing. But if you do that, suddenly you start to have incredible balancing capabilities. So now you have a robot. You're solving this problem at a kilohertz, and now you can start pushing your robot around, and you can adapt the behavior of the robot on the fly. So what you do here is you only optimize the next control. But once you do that, you cannot foresee the future, right? So you cannot say, oh, maybe I need to take a step in a little bit. So the next thing was to start to optimize trajectories. So instead of optimizing for the next best thing, you want to optimize to look into the future and say, what should I do this next 1, 2, 3 seconds? And how do I optimize that? So in order to do that, in my lab, we started to build specialized optimizers to be able to do that quickly. And if you do that well, you start to be able to have dynamically feasible trajectories like that you can optimize really quickly. But really quickly is not fast enough, right? Really quickly doesn't give you to real time. So then we worked a lot on how do you get into real time? And real time means that suddenly you break the barrier between what you do offline and what you do online. And this is what we call model predictive control. The model predictive control, you predict the future, and then you optimize what is the best thing you should do now, such that in 1, 2, 10 seconds from now, you will get the outcome that you want. And the moment you're able to do that, you can start generating very complicated behaviors. So for example, you can get a robot to walk. The robot that is, the biped is walking has no ankles, right? So it's actually very difficult to stabilize, but you can get it to stabilize, you can push it around, and it's always going to adapt. On the right side, I like this behavior because you ask the robot to reach the hand, and it finds on the fly, right, in real time at 20 hertz, what is a dynamically feasible behavior such that it can reach the hand and be able to still land on its 4 feet, right? So you can do that, and you can generate a lot of different trajectories. So now you optimize the next best thing, you optimize full trajectories. Well, the next step is to start optimizing functions directly, right? Infinite dimensional objects. And that's what deep learning allows you to do. So people are starting to say, now I want to optimize a policy, which is basically, how do I find a function that maps any possible situations into an action that I should do? So this is done with reinforcement learning, right? Policy optimization, that's really what it is, because you use a model with your simulator and you do optimization. This is back offline. So now we went to doing everything online to doing everything offline, and then we do nothing online, we just optimize our policy. But if you do that well, what is really amazing is that suddenly you can add perception to that. And that was the brick that we were missing, is the ability to add visual perception and multimodal perception into our control. And if you do that right, suddenly you start to have behaviors of robots where the perception is used to detect the obstacles and decide how to cross them, that are really, really complicated, right? So going full-blown to optimizing very complicated things and adding multimodal sensing really, really brought us really far. And here I draw this thing between what you can do online, and we spend a lot of time trying to do everything online and optimize a lot of things really online. And then we're kind of back to doing everything offline. I think really the sweet spot is in between, right? You really want to find what is the best way to do things? Can we pre-compute a lot of things? But online, we really need to be able to have some deliberation online and make decisions on the fly. Otherwise we'll be stuck when a problem happens. And one thing that we've not been very good at in leg locomotion, and I think Jens today, I was happy that he was talking about this, is how we do like what I would call real learning, which means not optimizing over a data set that is fixed, but let's say my robot walks, it falls. Can it learn how to not do the same mistake again? And all of the robots that I have, they walk, they fall, and they're going to do the same fall and the same stupid things until an engineer either adds a data point in the data set or tweaks a cost function and does something, right? So how do we get to the point where robots can figure out by themselves how to improve their behavior? So I don't think we know how to do. Okay. So here I made the case that the more you optimize things and the more complicated things you optimize, the more you get out of that. What is just that? Not really, right? The great hardware. So having access to amazing torque control hardware really made a huge difference in the field. And here I would like to emphasize the fact that having access to hardware is important, right? Having great hardware that you cannot buy is not really helpful. Now we start to have quadruped robots that are the cost of a high-end laptop, right? That makes a huge difference. And we also have a lot of people who spend time building learning frameworks, really good simulators, really good optimization algorithms. And all of that basically really made leg locomotion from a closed club of people who could have one to accessible to everyone, right? Everybody can start to do leg locomotion today. It was not true 10, 15 years ago. And because of that, we can take ideas to experiments really, really, really quickly. So now you have a lot of people having really, really cool ideas that they can test really quickly. And I think that's what really made the difference in the field these past years. So we also try to do that by building your own robots and things like that, and trying to open source things. You've seen most of the robots I've showed you today, they were actually part of an open source project that have been that I started a few years ago. The last thing, and I would like to stop on that, we have a lot of cool robots, they're walking around, they can do a lot of things. What are we going to do with them? Because it's one thing to have really nice robots, but it's another way to actually have a positive applications of them, right? Are we going to use them to do construction, to deliver our packages, to cook, to do firefighting? Are we going to put them as police in the police or in the military? All of these are actually, people are doing that these days. And I think as a robotics community, we should look at the technology, but we should also think what kind of world we'd like to see with those robots. Thank you so much for listening to me.
Thank you very much. I can accept short questions. Yes, please.
Hi, Ludo. Good to see you again over here.
Oh, hi.
Hey, a great talk. Thanks a lot. People over the last, I guess, 10, 15 years have always talked, or 20 maybe, have talked about the duality between manipulation and locomotion. But it seems, from what you were saying, that symmetry or duality is completely broken now. Is that right?
No, it's not right at all. I chose a title for my talk that kind of restricted what I wanted to show today. Actually, we use the exact same tools to do manipulation as well. And I think you can do optimization, you can do learning, and I really think I really think those problems are even closer today. I just didn't have time to show all of this work and all of the things that we do that. No, absolutely not. I think they're really connected a lot. And the next exciting thing is to start to do manipulation with like robots, right? No. So absolutely the duality is still here.
Great, thank you.
Thank you very much.